Hi, welcome to lecture 26. We're going to be covering section 5.2 in the Jayam book today. We're going to use, what is the point of that? We're going to be doing proofs by induction of formulas for both sums and products. So here goes. The layout today is going to be four sort of basic chunks. First, a little bit of talk about motivation. In the second section there, I'm going to show you two different sort of styles that you can apply for doing proofs by induction in this setting of formulas for sums. And then we'll run a bunch of examples. And then at the very end, I've got a couple of pieces of advice I want to harp on a little bit, but let's get moving. So the first, I think the classic proof by induction is of a formula that was discovered by Gauss when he was 7 years old. He's 7 years old, his first year, I guess, at elementary school. And who knows, but somehow this class was given this task. They were supposed to add up all the numbers from 1 to 100. I've always had this fantasy that maybe it was this German elementary school teacher who'd been out to the Oktoberfest all night and then just didn't want to deal with these bright, shiny faced kids in the morning. So it's like, oh, go add up everything from 1 to 100. And then little Gauss comes up, a minute later, and he's got the answer. So, yeah. One other thing, just placing yourself in the history of this a little bit, imagine what they were working with in 1784. And that's a time when paper was still, a very precious commodity, so little kids didn't get to use it for their schoolwork. They'd begun the process of sort of, modern manufacturing of stuff, but it wasn't really there yet. So things like paper were often made by hand. So what kids had at that point was a chunk of rock that's known as slate. Um, it happens to come in very fine layers, so you can get chunks of this slate rock that are maybe a quarter of an inch thick, and it has a black surface on it, and you can mark it with chalk. In fact, when people talk about blackboards, what we ordinarily see in a classroom today is either whiteboards or they're green or something. But blackboards originally were big, large sheets of slate, and that rock is colored black. Anyway, a kid would have a little chunk of slate, and they also would have a piece of chalk, like the rock that people dig up out of the ground chalk. The modern chalk that we see that comes in a little stick, that's manufactured. This is a rock that is known as diatomaceous earth. But it was scrawling on one rock with another rock. That's how they were doing their scrap work. Anyway, Gauss came up with this thought, and it's clever. He said, look, I can sort of pair these things from the two ends, 100 with 1, and then 99 with 2, and then 98 with 3, and so on, right on down until we get down to 50 and 51 would be paired. So by pairing things like that, I have 50 pairs, and each of them each pair has 101 in it. Okay, so 50 times 101, well, even a 7-year-old could do that multiplication because of the 0 on the 5. So he comes back with 5050, and that's the correct answer. Now, that particular scheme of doing a pair up, that only works because 100 is an even number. So I'd like to mention how you do this more generally so that it still flies when you've got an odd number, but it's essentially the same idea as what Gauss did. It's called double counting. So you're going to write the sum down twice, and there they are. One on top, I'm going up, and on the bottom, I'm going down. All right, so if you look at the columns here, well, there's n of them, right? I've gone general now, right? I'm not going to 100, rather I'm going up to n. And there's n columns, and in each column, do you see that we have n plus 1 is the sum? It's easiest to see at the beginning, at the end. But in the middle, n minus 1 plus 2, that's n plus 1. N minus 2 plus 3, yeah, that's n plus 1. So all of those columns total n plus 1, and there are n of them. That's the double of our sum. Here's the formula. The sum that goes from 1 to n of k, just adding up the integers k, is 1/2 of what we would have just gotten by double counting, n times n plus 1. N columns, each of which added to n plus 1. That's kind of cool. Anyway, another piece of motivation, this was probably more of a motivation kind of back in the day, but it's still motivating, I think, to a certain extent now. Riemann sums. You know that a lot of times when you go to do integrals, well, it's impossible. It's often the case that there simply is no closed form solution to an integral problem. You know that a lot of integral problems are super hard anyway, and there's a workaround. You can always do Riemann sums to get a numerical approximation to an integral. So, so we'd like to take advantage of that. Uh, and the basic theory that lets us take advantage of that is what's written right here. It's a linearity property of integrals. You may have seen this expressed different ways. Sometimes people break it up into multiple rules. Like there's the sum rule for integrals and the product rule for integrals. And well, this is taking it all at once. If you have what's known as a linear combination, some multiple times f of x plus some other multiplier times g of x, you want to integrate a thing like that, it's fine. You just carry the multipliers along. They can come out of the integral because the multiplying by constant doesn't really have a huge effect. It's just scales thing, and so you just scale the answer. Anyway, you get a separate integral of f of x scaled by a and a separate integral of g of x scaled by b. That's actually a fairly common way to express any operation being linear, that you can kind of distribute it across a linear combination like this. Okay, so because of this rule, anything that's a polynomial, we can integrate, so long as we know what the integrals of the powers of x are. And if we translate that to Riemann sums, that means if we can do the Riemann sums for powers of x, we'll be able to get numerical approximations to these integrals. And polynomials, that's a slightly restrictive class, but anything at all can be expressed as a polynomial up to a point. A Taylor series, or a truncated Taylor series, provides you with a polynomial that closely approximates the function in some interval. So, for numerical purposes, it's often good enough to use a polynomial approximation to a formula or a function that you're interested in, and then use Riemann sum ideas to get the integral. And all of that just relies on us needing to be able to do the integrals of powers of x. So when we talked about Gauss's trick, or the generalization of Gauss's trick, that gets us an integral formula. That's exactly the integral of x. It's because that j in there is just j. It's just the summation variable. It's the identity function applied to the index. Okay, so let's take a look at a Desmos graph here. That's not Desmos. That's Desmos. Make this a little bigger so we can see it well. Maybe shrink the stuff on the sides. Well, what I've got graphed there is y equals x squared I'm really looking from 0 to 10. In fact, what I'm going to do is figure out the area under the curve between 0 and 10. You may have seen this before. One way to do that is with what's known as a left-hand Riemann sum. So I'm shading in the Riemann sums. This is the area under a constant that is determined by what's the value of the function at the left side of a little subinterval. So that one, it's 81, because the left side of that interval is 9. What I'm looking at here in shading is 0 plus 1 plus 4 plus 9, 16, 25, 36, 49, 64, and 81. And I think you can look at that and go, well, yeah, that's not horrible, but it misses quite a lot too. There's all this white triangle area that's above the blue shaded area, but below the graph, so we'd be off by that. So there's a pretty standard trick we do then, which is do the same thing. I wanted to reveal it. Let's do the reveal again. Do the same thing using the right Riemann sum, where you get the value of your constant over each little subinterval looking at the right-hand side of the interval. Now the two of those together, one's an underestimate, the other's an overestimate. So they come, if you average them, you get a pretty good estimate. And visually, the average of those two things is this thing, which is known as the trapezoid rule. Let me again do the do the reveal. It just looks like it's the area under the curve, doesn't it? Well, if I zoomed in a little closer, down here near 0, where you can see that the blue thing is curved, but the red things are straight, you see it's not identical to the area under the curve. It's a little bit of an overestimate, but it's very close. And if you put yourself back in your Calc 2 days and remember there were error estimates on the Riemann sum approximations. So we can get, we can at least know how far off this could potentially be. And just if it's not good enough, you just subdivide more. Instead of, I've got 10 divisions between 0 and 10, make it 100, and you'll get much, much closer to the thing. And of course, that's at a certain amount of expense in terms of doing work, but, well, that would have been a hard thing in Gauss's time, but for us, computers will just knock this out. All right, so trying to convince you that Riemann sums are a useful tool for getting numerical approximations of functions. So what does that mean? Well, we've got the formula for x, and we're going to need formulas for the sums of squares, for the sums of cubes, and so on. Okay, so first powers. This is just k to the 1 power. It's being added up from 1 to n, k to the 1. It's Gauss's formula. Squares are second powers. Much tougher. Well, not a whole lot tougher, but it's tougher. The fraction went from a half to 1/6. That's sort of intriguing. Notice how there's n and n plus 1 in both of them. That one's got an n and an n plus 1. That one's got an n and an n plus 1. It's kind of like, a lot of the same features are there, but this one's also got an additional 2n plus 1. But yeah, if you add up the squares of the numbers from 1 to n, you'll get this thing that you can write in terms of a formula for n, a formula for it in terms of n. And then cubes. And I don't know, usually in calculus textbooks, they have these 3 formulas laid out where you're doing the Riemann sum stuff, and you're supposed to memorize them. At least, I think most people, if you do memorize it, you memorize it for the sake of the test, and then you clear that memory space out. But the memory trick here, which is kind of mind-boggling if you think about it, is that this bottom formula is exactly the square of the top formula. Can't highlight like that. You see how 1/2 squared is 1/4, and n squared, n plus 1, n plus 1 squared. So the sum of the integers squared is the same as the sum of the cubes. Freaky. Yeah, it's a weird factoid, but it's true. And kind of it might be an interesting thing for us to try to prove at some point. Okay, more motivation if you hadn't had enough yet. Jacob Bernoulli is one of this mathematical family. The Bernoullis, there was like, I don't know, 8 or 9 of them, I think. Probably more than that, but 8 or 9 that were famous. And it looks like there are more than that because some of them had multiple names that they got published by. Like Jacob was actually also called Jacques if he published in French. And I think there was a James if he was in English. I may have that wrong, but I think he had at least 3 names, and several of them did. So anyway, Jacob Bernoulli took that whole idea about Riemann sums and kept going. And he developed a table of formulas for the sums of powers all the way through 10th powers. So beyond cubes to 10th powers. He showed in general how to come up with these formulas using what are now known as Bernoulli numbers. I don't believe he named them Bernoulli numbers, but they now go by his name. And it's a little complicated, but it's not crazy. You can. It's a good like undergrad honors thesis topic to investigate this. Actually, anyway, here's the formula for the sum of the first n 10th powers. You might look at that and go, okay, that's pretty bad, but you should notice that it's got a lot of the features that we saw back in the cubes or the squares. Or, well, you see how you've got a factor of n and an n plus 1 and a 2n, and a 2n plus 1. Those are all still there. We previously had 1/6 was the coefficient out front. There's a 1/66. Well, I'm not too surprised that the number's gone up a bit. Remember, it went from 1/2 to 1/6. Now it's made it way up to 66. The only thing that's hairy in here are these other 2 polynomials, these other 2 factors of the polynomial here. n squared plus n minus 1, and this 6th degree polynomial that I'm not going to read because it looks like it's random, doesn't it? But it's not. You can deduce what this is from Bernoulli numbers. Anyway, this is what Bernoulli had to say about his formula. Although he probably wrote it in Latin. But with the help of this table, it took me less than half of a quarter of an hour to find that the 10th powers of the first 1,000 numbers being added together will yield the sum. Yes, that's the sum. In like the 1700s, he does this by hand. That's pretty fancy and fast. Think about that, 7.5 minutes. He's half of a quarter of an hour. I couldn't do that. I'm quite certain, but I can do it in way less than that if you let me have Sage. So here, let's pop up in a Sage worksheet. All right, so the hairy polynomial, I've already typed it in here. The 3n to the 6th plus other stuff is all typed in here. Because I had typed it in previously in the slides, so I had the variable was n there. I just changed the variable in the Sage worksheet to be n, so we can deal with that. Now that's not going to do anything, right? That's just because there's nothing that's printed or anything. All I'm doing is assigning that polynomial expression to the variable p. Okay, and it was delaying not because that took a lot of time, but because I let this on pause for too long and it had lost its connection to the server. So this is Sage syntax for substituting a value into an expression. It's the member function of the variable p. P is this expression involving a single variable n. So you can see p dot subs and then give the value you're interested in. And that's the number that Bernoulli would have gotten for that thing. And possibly, it looks like there's a lot of zeros in it. Possibly the form of the number he was working with, n equals 1,000, may have made this computation easier, even if you're working by hand. So the other thing I just happened to guess at, and it turned out to be true, was that 66 would divide into all those other factors that we saw there. You can see that n and n plus 1, amongst the two of them, one or the other of them will be even. And when n is 1,000, this number, 1,000 plus, 1 million plus 1,000 minus 1, well, I think I checked and it was divisible by 11. And then there's some other trickery to get that there's a 3 that goes into one or the other of these. But if I guessed that this was the case, and you can't see yet, but once I substitute in 1,000, you see how the dividing by 66 did not create a fraction out of it. So it must be that the rest of those factors were divisible by 66. So now that's great. All we have to do, if we were Bernoulli, we have to write down this, 20-digit number, and this one that's maybe 12. I should count it, but that's more than 12. 13 or 14. Anyway, it doesn't matter. Let's just multiply them. I previously copied them into the sheet. So there you go. 914099242. Is that what the guy said before? 914099242. I'm not going to check every digit, but I think we got it. Or I think he got it. If you're into Douglas Adams at all, it's kind of funny how many times the number 42 appears in this. They're just everywhere. Yeah, lots of 42s. Okay, so that little spiel was meant to be motivation, why we'd be interested in having formulas for sums. Now that we're going to do it, I just want to point out there's a multitude of ways you can organize things, or there's at least two. So we will, let me get this out of the way. We will run through what the two approaches essentially are, and then we'll do some of the examples. We'll do one way and some the other way. Okay. So I'm using the abbreviation IH up here in the slide's title. That's inductive hypothesis. Good? Yeah. So this first approach is going to use the inductive hypothesis somewhere along the way in doing the proof. You can take a sum whose upper limit is k plus 1 and break it apart. You just create two parts out of it. One part is easy. It's just whatever the k plus first term would be And the other piece is all the rest of them. Oh, I can't highlight like that, but this sum on the end, still can't highlight. That just goes to k. That's the first k terms of this guy on the left, and this is the last term of this guy on the left. So these two together are the same as that. Well, why would you do a thing like that? It's because you're trying to show that the formula being correct at stage k implies that it would be correct at stage k plus 1. And this is exactly stage k. This guy at the end, the sum that goes from 1 to k of whatever the formula is in there. So we'll be able to use the inductive hypothesis on that guy. So when you're doing this approach, just a sort of a caveat or a thing to remember about it, usually you're not going to be working with equations, but rather with one side or the other of an equation. That's sort of a clue as to how things are going. If you're working with the expressions that appear on one side or the other of an equation, then you're probably doing this strategy. So what's the other approach, the other alternative approach? Frankly, I've taken this to be my favorite approach. I usually go with this first. You start with the inductive hypothesis. You just say, well, here's the inductive hypothesis. We know that this is true for the sake of our argument. And then you have to figure out how to change the inductive hypothesis into the inductive conclusion. So that means figure out what to add on both sides so that you'll wind up with the inductive conclusion. Usually the algebra involved in these two methods or these two approaches is exactly the same, possibly just, slightly organized differently, but more or less the same. And there's no preference. Either approach is fine. It's a matter of taste. If you're doing this second approach here, you'd generally be working with equalities on each line. You start off with the inductive hypothesis, which is a sum is equal to a formula. So it's an equal sign in between two things. And then you'll end with the inductive conclusion, which is of the same shape. We've got an equal sign with a sum on the left and a formula on the right. So let's run some examples. Figured we'd start with Gauss's thing, that for every natural number, only for positive natural numbers. Do you see why I wouldn't want to let n be 0 in this one? The sum is going from 1 to 0. That'd be an empty sum. Actually, it would work, turns out, but let's not boggle our brains about empty sums until we get into the activity for this section. So if you've got a sum where the upper limit is 1, this sum here would just have a single term in it. But anything higher than that, you're going to have n terms. Anyway, this sum is equal to this formula, n times n plus 1 over 2. So how's a proof going to look? It's a proof by induction, so you're going to tell people that you're doing induction and generally tell them what variable you're inducting on. Proceed by induction on n. And then the layout of induction proofs is almost always, here's the base case, and then here's the inductive step. Just boldly write down what you're doing and then do it. So it says both the sum and the formula evaluate to 1 when n is equal to 1, colon, and it shows them separately. I really want to emphasize to you that you should do these two things separately. Figure out what the sum is when n is 1, and figure out what the formula is. This is, by the way, are you familiar with this notation of I can't highlight it, a bar with a value of the variable down as sort of a subscript to indicate evaluation? This is saying take that formula and evaluate it at n equal 1. You've used this notation before, except you usually had a lower limit and an upper limit. That's the same vertical bar you see when you do a definite integral. So that's how you can express that you want to add up, you want to evaluate the formula when n is 1. And it just becomes 1 times 2 over 2, which is 1. But we do these things separately and then just sort of point out to our reader that we got the same result in each of them. All right, then the inductive step. Well, I'm doing this one by the first mode. We'll start by just thinking about the sum that goes from 1 to k plus 1 of just the integer j. The index variable is unmodified in there. You can separate out the last term of this sum. So There's a little bit of a typo here. That probably shouldn't say equal, but rather just k plus 1 plus sum of k plus, where this thing is equal to it, but it shouldn't have a dangling equal like that. All right, anyway, we're going to next use the inductive hypothesis to replace the sigma part here with the formula. So what do we get? I'm going to reveal this a step at a time. The sum from 1 to k plus 1 broken apart into k plus 1 plus that, just the sum that only goes from 1 to k, which is equal to k plus 1 plus that formula. Here's where we've used the inductive hypothesis. By the way, always a great idea, once you've finished a proof by induction, go back afterwards and ask yourself, where did it happen? Where did I use the inductive hypothesis? Because if you got it done without using the inductive hypothesis, that really casts doubt on your result. You've probably fooled yourself, I'd think. All right, then what are we doing? Algebraically from here, we're just putting things over a common denominator, combining them, and then notice that both of the things in the numerator had a k plus 1 in them. So you can factor that k plus 1 out, and you get 2 plus k, which I've written as k plus 2 because that's the way we usually write it. Well, that's what we wanted to have, because that is our formula with the n replaced with k plus 1s. So you get to say QED right there. Now, I did not do something which I normally advise students to do in this proof, which is write down a we want to show sentence, or at least somewhere on scrap paper, write down what it is you hope to show. Let's back our way up to the statement. Oops, there it is. What you're hoping to do is get this equation that involves a sum and a formula when n is k plus 1. So that'll be a k plus 1 times a k plus 2. And that's what we got on the bottom of this page right here. K plus 1 times k plus 2 over 2. QED. I want to do this again because I'd like to illustrate the other approach in this nice simple setting, as this is probably one of the simplest inductive proofs we can do. The base case is going to be the exact same thing, so we won't do that part, just jump to the inductive step. So in this one, I know right away where I use the inductive hypothesis because it's the very first thing I write down. Just say, okay, here's the inductive hypothesis. And we got to figure out what to add to both sides of this so that we convert the sum that's on the left to one that goes all the way to k plus 1. In other words, we need to add that last term in it. But in this case, the summand is just the index variable itself. So adding k plus 1 itself is the thing to do. So here, I've just added k plus 1 to both sides. Not done any reductions yet. Now I've done a reduction. Thus, that's the reason we added that k plus 1 on both sides was so that we could make the sum go all the way to k plus 1. So there it is, written that way. We're still adding j, but we take it from 1 to k plus 1. I haven't done any simplification on the right-hand side yet, but we will. Find a common denominator, we'll put it over that denominator. I think I skipped a step, but you've seen the algebra before, so QED. Often this feels to me a little easier, but it's a big world out there. Do what you prefer. You have to get used to adding the correct thing to both sides of the inductive hypothesis. And there's, for some reason, after you've done that one and maybe only a few other ones, you get the idea that what you're supposed to do is add k plus 1 to both sides, always. But that only works if the index variable is appearing unchanged inside the sum. If the summand is just the index variable, that's what you would add, but not usually. So don't do that. That's what we added in the last proof, but that's, that proof is basically the only time you would use just k plus 1. What you really have to do is go look at the formula that appears after the sigma sign. How is it modifying the index variable? What formula in terms of the index variable, are we adding up? And apply that formula to the number k plus 1. So we'll see that here in an example. I'm going to run the sum of cubes for us next. That was one of the ones we saw in the Riemann sums intro. All right, so I'm talking about quantified over positive natural numbers, which again, that makes sense since the sum runs from 1 to n, having n be 0 or smaller would mean the sum was empty. So we could do that, but it's kind of nicer to start with a sum that at least has a single term in it. So notice that when n is 1, this would just have a single term, and it would be 1 cubed, 1. Anyway, we saw this formula before, too. Remember, it was the square of the one that Gauss came up with? So here's the proof. Proceed by induction on n. N is the upper limit on the sum, just to think about what it is we're inducting over. Our base case thing, like I've done before, is going to be just a verification that the sum and the formula for the sum give you the same answer when n is 1. So if I add up the cubes from 1 to 1, that's only one number, 1 cubed, so that's 1. And if I evaluate this formula when n is 1, it'll be 1 squared plus 2 squared over 4. That's 1. So the inductive step is going to be tougher this time, but it's not crazy. We can work with it. Just stating the inductive hypothesis first. Here's my we want to show sentence, because I want to have somewhere on the page what it is I'm trying to get to, because I've got to strategize to arrive at this sum that goes to k plus 1 equaling this version of the formula, where all the n's have been replaced with k plus 1s. But I don't want to make it look like I'm just assuming that, right? So I put in this little preface. We want to show that. That just means it's a remark, right? It's not part of the flow of the argument. Okay, so now we're doing the argument. I'm going to add k plus 1 cubed to both sides. Because why? The sum involved cubes, and to get the last term in that sum, the k plus first term, I need to add k plus 1 cubed. All right, so first I'm just adding k plus 1 cubed symbolically, not even doing any algebra to that. But then let's work on that a little bit. The thing on the left is indeed the sum that goes from 1 to k plus 1 of cubes. I haven't done anything to what's on the right, though. We'll just left that alone. But let's work on it now. Put it over a common denominator. So I have to take that k plus 1 cubed and multiply it by 4 so that I can put it over to 4. It's the denominator from the other fraction. That's good enough. Now, do you notice that I got to give you a little piece of advice in here. A lot of times people will tend to just work out what this is as a polynomial, that is, expand that sucker. And that isn't necessarily wrong, but it's going to force you into the working forward and backwards from the conclusion mode. And a lot of times you can take advantage of factored form. So do you notice that this one has k plus 1 cubed in it, and this piece has k plus 1 squared in it? So both of them have k plus 1 squared. So what I'm going to do next is factor out a k plus 1 squared. That leaves behind 4 and 1 more k plus 1 in the thing on the left, and just k squared in the thing on the right. Well, that's k squared plus 4k plus 4, just working out what's in the parentheses there, times k plus 1 squared. Do you recognize that? Sorry, it kind of goes off the page here, but at least you can see the top of the fraction. Yeah, k squared plus 4k plus 4 is k plus 2 squared. And that's what we wanted to get to. So even farther below the bottom of the screen, there's a QED right now. You can't see it, but it's there. All right, another example, because the more of these we do, the more facile we'll get with it. Back in the, spelled it wrong, but the exercise 1 in section 5.1, it had you looking at the truth of this result about, it's kind of a weird thing. You're adding up numbers of the form 4j plus 1. So things that are 1 bigger than a multiple of 4. And starting with j equals 0, so that would mean this formula gives you 1, and then keep going until n, and then you'd get 4n plus 1. Anyway, that sum of a whole bunch of things that are 1 mod 4 can be re-expressed as this just polynomial in n. Quadratic polynomial. It's weird. So now that we hopefully spent some time looking at this before, and you know it's actually right, or you believe it's right, you can prove it for all n instead of, what we did before was just try the first several values. Maybe it works at first, but then it breaks later on. When we do an inductive proof, we know for a fact that it works forever. So I've just written the thing as a theorem. This is quantified over natural numbers. Is that correct? Yeah, because n could be 0 in this one. In fact, that's the smallest value of n that makes sense. If n was 0, we'd have a sum with a single term in it, and it would be 1. And that's the formula that we're getting. Well, that's good. All right, so yes, we'll proceed by induction on n. What's the basis look like? Well, I've split it up a little bit. I put a pause in the middle of this, but when n is 0, the sum from 0 to 0 of 4j plus 1, yeah, like I said, that's just 4 times 0 plus 1. There's one term in that, and so you get 1. And what about the polynomial? If you evaluate when n is 1, you get, I copied wrong. We're not evaluating at 1, we're evaluating at 0, right? I'll fix that in the slides before I post them. But yeah, this would be n equals 0 that we evaluate, because 1 would give us something like 6. Is it right? But yeah, 6. But when n is 0, these terms go away, and you just get that 1. All right, so my anal retentive nature got the better of me. I had to fix that before I left it. So this is the correct statement. When you have the polynomial evaluated at 0, you get 1. Okay, so that's good. The base case is handled. We now move on to the inductive step. Here, the inductive hypothesis is, well, just that the formula works for the sum when n is replaced with k. Really. What we want to show is, wow, the sum of 4j plus 1 that goes from 0 to k plus 1 would be equal to the formula with k plus 1s in it. But just to help us later, let's work out that that's equal to 2k squared plus 7k plus 6. I'm just expanding this FOIL rule, that one, and then add on combine the similar terms. And trust me on this, you get 2k squared plus 7k plus 6. So what we're going to need to add to both sides is the k plus first term, which is 4 times k plus 1 plus 1. Don't know why I didn't write that as 4k plus 5, but, well, because it looks more like you're adding the k plus first term right now before you do any simplifying to that. All right. Well, where do we go next? Just simplify this to 4k plus 5 and add it to this. And you get 2 times k squared plus 7k plus 6. Is that familiar to us? Oops, went too far. Still went too far. There it is. We want to show sentence ended with that form for our thing. So cool, we made it. We're in the right place. We can write QED at the bottom of the page. Okay, we've done a couple of examples with sums. I want to do one with a product as well, just to, we should be able to do either. Honestly, they're the same process. It just, where before we added, here we'll multiply. Yeah, the only difference is if you've got a formula for a product, it's going to involve multiplying both sides by the k plus first term, or that other move where you pull the k plus first term, factor out the k plus first term from the product. So we'll practice on this. The product of j over j plus 1, where j is running from 1 to n, actually simplifies to 1 over n plus 1. There are other ways to see that, but here's a proof by induction. So start it off with the boilerplate language that you're going to go by induction on n. Show in the base case, when n is 1, the product here just has a single term in it, right? So we're multiplying the one number, that is 1 over 2, and we get 1 over 2. When n is 1, the formula evaluates to, well, also 1 over 2. So those are equal. Done. The inductive step, how does this look? The inductive hypothesis is written here. Well, I guess I'm going to do the one where we start with the inductive hypothesis and kind of apply something to both sides of it. Here's a we want to show sentence, but the we want to show is pretty easy. Just the k's become k plus 1s, and k plus 1 then is going to become k plus 2. Okay. Oh, no, I didn't. Apparently I wrote it in the other form. So consider this product beginning with j equals 1 going up to k plus 1 of j over j plus 1. Fine. Note that you can split it apart. You can factor out the last term in the product. And it's, of course, that would be k plus 1 over k plus 2, because it's the form of number over the number 1 bigger than it. So when that number is k plus 1, or k1 over k2, k plus 1 over k plus 2. And then this, what remains is the product of all the other k terms from 1 all the way up to k. So this is sort of the bigger of the two things. This is k things multiplied together, and that's 1 more. Using the inductive hypothesis, you see this piece on the right here, which I can't highlight properly, but I can kind of indicate somehow that that's equal to something because of the inductive hypothesis. In particular, it's equal to 1 over k plus 1. So we're just subbing that in. Replace the product from 1 to k with 1 over k plus 1. And then do you see how it cancels? There's a k plus 1 in the bottom, a k plus 1 on the top. You end up with 1 over k plus 2. I think there's a QED that's off the bottom of the page. But, well. All right, so you've seen some examples of each sort. Let's say a little bit about general ideas here. Notice that the way I did the base case in all of these, I was very careful to do the sum is equal to one thing and the formula is equal to another thing, and then compare them. Do it that way. For some reason there's a tendency for people to just write out this thing is equal to that thing, and it just looks like you're assuming the conclusion that you're trying to reach. You have to be demonstrating the conclusion you're trying to reach, which is just the two things are equal to each other. So evaluating them both and seeing separately that they have the same value, that's the way to go. You don't have to do what we want to show sentence, but it certainly doesn't hurt. Sure. But this is true. At least write down the inductive conclusion somewhere on a piece of scrap paper. If you're working on a chalkboard or something or a whiteboard, write it up in the corner and put a box around it. Make sure nobody thinks that that's part of your argument, but it's there to guide you that that's where you're heading. You're trying to reach that inductive conclusion. My advice is that you should try to do both of these ways we've illustrated, because there's sometimes when one or the other is sort of more appropriate. Not necessarily for formulas involving sums, or sums, the formulas for sums, but it occasionally is the case that one or the other of those will feel better. So be able to do them both ways. It's perfectly fine to develop your own favorite, though. If you see most of the time you want to do the writing the inductive hypothesis down first form, that's fine. Nobody's going to care. Lastly, you got to practice. There's just no way around it. If you don't do a mess of these things, you won't learn. So you've got to try a bunch of inductive proofs. And you have to have a certain level of honesty with yourself about them, because here's the deal with an inductive proof. In the inductive step, you know where you're supposed to go. Right? You know you're trying to reach the inductive conclusion, and you know what it's supposed to look like. So you could fake it. You could. You could just write down a whole bunch of algebraic mumbo jumbo and then go, at the bottom, it comes out miraculously to the right answer. Of course, your professor's likely to notice that you did that. And plus, you yourself ought to notice that you did that. If you can't get your algebra to finally reach the inductive conclusion, that means probably one of two things. You did something wrong in the algebra somewhere, or maybe the setup wasn't quite as smart. So, but practice a bunch of them, see that they work out, and you'll master this technique. It's not rocket science. It might lead to rocket science, but it's quite doable, and it's great because it's like a machine. You just turn the crank, and out comes a proof for the formulas for sums. That's a good way to put it. There's just no way to get the zen of doing an inductive proof without doing lots of them. Once you've done a bunch of them, this just flows off your pen as you're trying to write these things. All right, well, that is the end of today's slide deck. we'll be doing some more inductive proofs next time. We'll be in section 5.3. Uh, there are lots of things that we can prove with induction, and they don't have to be formulas for sums or formulas for products. And what 5.3 is about is showing us some of these other things that you can prove inductively. A lot of it is divisibility formulas, but there are things like inequalities that can be proved by induction, and some things that are just sort of weird that we can prove by induction. So reading 5.3 ahead of time would be awesome. I hope you come prepared for the next lecture. And in any case, hope you have a great rest of your day.